Hi, I'm Dr. T, and welcome to my desktop. So today I'm looking at fatty acid metabolism. So both the catabolism, which is called beta oxidation, and the anabolism, which, fatty acid synthesis. So this article has a nice little diagram down here that I'm going to kind of walk through. Okay, so you're going to get your fatty acids probably in the form of triglycerides. So in this case, you've got it in a nice fat cell, big old fat droplet of triglycerides. You're going to take those, you're going to take the glycerol, split that off, you're going to have the free fatty acids. Now, this could be also coming straight from your stomach, small intestine, or elsewhere. So it doesn't necessarily come from a fat storage cell. Now, these are going to be transported from wherever they are from via a serum albumin. These are a fatty acid transport protein. They're a major component of blood. Okay, so we're going to have an albumin protein. It's going to transport your fatty acid. That's going to get inside the cell, at which point then we're going to start processing it. It's going to get eventually shoved into the mitochondria, where the beta oxidation takes place. And the reason it's called beta oxidation is we're reacting with the second carbon after the carboxylic acid. So the fatty acid gets acetyl-CoA stuck to it. Well, not acetyl-CoA. It's going to turn into an acetyl-CoA. It gets a CoA stuck to it. So that would be the acid carbon. That's the beta, that's the alpha. And then that's the beta. And what we're going to do is we're going to start reacting the beta carbon, and that's going to involve eventually breaking the bond between the alpha and the beta. And then this will turn into acetyl-CoA, and that can go into citric acid cycle and get tons and tons of energy. And then you have a 2-carbon shorter fatty acid. Most fatty acids are an even number for reasons that will be very obvious on the next page. Okay, so a couple of quick things. Again, we got some reduced electrons. We got some nice high energy electrons over here. We get a little bit of ATP, not a lot, but that's actually more than we get from glycolysis. So, I mean, this is actually pretty good. And, we just barely dented this. So fats are going to have a ton of energy. Anytime you make acetyl-CoA, that's going to give you a lot of energy, because when you're looking at things like glycolysis or even the beta oxidation, these are giving you a modest amount of energy. It's really those high energy electrons, electron transport chain, and the citric acid cycle, and then taking those high energy electrons and putting them through the electron transport chain. That's where you get a ton of energy. So yeah, we've got this. By the way, that's also why ethanol has so many calories into it, because it hasn't gone through electron transport chain, or I shouldn't say it hasn't gone through citric acid cycle. So it can still do so. The yeast did not take much energy out of it, so almost as much as was in the sugar. And of course, if you make acetyl-CoA, which is what's going to happen to that ethanol, after a little bit of post-production, it's going to be turned into acetyl-CoA for metabolism. Hey, you could just use that acetyl-CoA. You need it for energy? Great. You need it to make fat? Let's just make some fats. That's one reason why heavy drinkers tend to, gain a little bit of weight. They're eating a lot of calories, and it's very easy for their cells to make that into fat. Okay, let's go into fatty acid synthesis. Unfortunately, nowhere near as nice of photos. Here's the pathway for this one. I've definitely seen some better photos on the internet before, but those are copyrighted, where thankfully we've got Creative Commons over here. Okay, so what we're going to be doing, essentially, the key part here is this actually kind of looks a little bit cyclic in nature, where we are going to be essentially adding a acetyl-CoA. So we're going to take our fatty acid chain, and then in the process, we're going to add an acetyl-CoA to this. And I do realize this is not the most clear. So this way, we're going to grow them 2 carbons at a time. So we're basically doing the reverse of beta oxidation. Somewhat different steps, but the reverse. Now, you'll notice when we looked at beta oxidation, we've got NADH2. When we look at fatty acid synthesis, we have NADPH. The P is a phosphorus. It's stuck on the other end of it. It does not affect the chemistry at all. But what this does is allows the cell to separate out its high energy electrons into ones that it's going to use for fuel, that eventually turn into ATP, and then ones that are used for synthesis. So they'll have somewhat different origins. Cells will modify things like carbohydrates and has a slightly different pathway than what we discussed to get NAD pH when they need that. But the goal here is, once again, to have 2 accounts, basically, and it's keeping its accounts of high energy electrons separate. So yeah, that's kind of the gist of fatty acid synthesis. The long story short is it's adding 2 carbons at a time, basically like the reverse of beta oxidation, even though it's not. And then, of course, we can do things like add double bonds to it, depending on what kind of organism you are, where you can put those on. And they are made tail first. So the tail of the fatty acid is made first, and it grows towards the head. Or, you keep adding on to the head part. That's why we can elongate them. And why the omega nomenclature is so valuable, because it's very easy for the cell to say, okay, I have a 16 omega. And the 16:1, that means you have 16 carbons and 1 double bond, is what it's saying. And then the double bond is 7th from the end. So it's easy to take the 16-1 omega-7, turn it into an 18-1 omega-7. It'd be much more work to actually move that 7. Okay, so yeah, that's fatty acid synthesis. Let's see if I can stop clicking. And I will see you next time. Have a wonderful day.